Hello and welcome to the third video of the M2 chapter Centres of Mass. Start a question on the screen to review the work so far. Find the coordinates of the centre of mass of the particles with masses these at positions these, respectively. This is very similar to one of the questions we had in the previous video, but I've changed it ever so slightly. So we've got on one side the total mass 4 plus 2 plus 8 plus 6 times by the coordinates of the centre of mass, x bar, y bar, is equal to the individual ones 4 times by its coordinates, minus 1, 3, plus 2 times its coordinates, minus 2, minus 4, plus 8 times 4, 0, plus 6 times 1, minus 3. Now when I did this in the previous video, I had g's all over the place because I was thinking moments and I was doing weight instead of mass, but that was making more work for myself because the formula doesn't actually use g because that always cancels out. So let's have 20 x bar y bar is equal to 30 minus 14. Divide both of those by 20, giving us x bar y bar is equal to 3 over 2 and minus 7 over 10. So the coordinates of the centre of mass, g, 3 over 2 minus 7 over 10. In this video, we are going to look at the centre of mass of some standard uniform plane laminas. And of course, first of all, we'll investigate exactly what this means, and then we'll look at a few different types. So you need to remember the results for the centre of mass of some standard uniform plane laminas. Uniform, I hope you remember from your M1 work, means that the mass is evenly distributed throughout the shape. Plane should also be familiar to you. That just means a 2D shape. And lamina is a shape modelled as having 0 thickness. Now that's very important. One of the consequences straight away is that there must be 0 volume. This of course is not a realistic real-world thing, but is a very useful model. So as indicated here, one of the consequences is that a uniform plane lamina has area, but no volume. And the mass is distributed evenly. These two things together means that the area is representative of relative mass. Let's quickly discuss this a little bit. So something in real life that is kind of close to a lamina is a piece of paper. It has quite a large length and width compared to its thickness, so much so that the thickness really is negligible and is almost considered to be 0. Now, like I said, you can't really have 0 thickness even for something as thin as a piece of paper in real life, but because it's so much smaller than the other dimensions, we can model it in that way. Now if we assume that that piece of paper is uniform, then the more of the paper you take, the more mass you're taking. If you split the paper in half by area, then you're also splitting it in half by mass. If you take a little corner off the end, then you're just taking a small amount of mass. So what this here is saying is basically more area equals more mass. And that's particularly useful when we come to do the next video, but it's also useful right now as we consider some of these shapes. So I've put that at the top of the next screen as well. That's the same statement. For uniform laminas, this is very important throughout this video, these are uniform laminas. That means that the centre of mass must be somewhere along a line of symmetry. Like I said, if you take half of the area, that means you're taking half of the mass. And of course the centre of mass will be on the line where half the mass is on one side, half the mass is on the other side, then of course it will balance on that line. If there is one, but many of our standard shapes will have a line of symmetry. And it must be on all the lines of symmetry if there are more than one. And that's particularly helpful because some of our shapes will have more than one line of symmetry, and where those lines of symmetry intersect is where the centre of mass must be. Again, for uniform laminas. So we can use this to locate the centre of mass for laminas of standard shapes. And we're going to go through a few that you need to remember. Firstly, the rectangle. You know that a rectangle has a line of symmetry down the centre here, and across the centre here. So the centre of mass, G, must be at the geometric center of the rectangle. For a circle, of course, we've got many lines of symmetry. I say many, what I really mean is an infinite number of lines of symmetry, and they will all pass through the center point of the circle. So as with the rectangle, the center of mass of a circle is at its geometric center. For an equilateral triangle, we have a line of symmetry along here that cuts through this side exactly in half through this vertex, down the middle here from this vertex, cutting the base exactly in half, and a third line of symmetry cutting this side in half, going through this vertex. So again, where those lines of symmetry intersect is our center of mass for the triangle. I think these three are pretty easy to remember. Geometric center of a rectangle, of a circle. The equilateral triangle has a point that most people would think of as its center, and this actually has a particular name, which will be important for what we're about to go on to. So let me stop to give you a bit of information. These lines here, they have a name, and that is a median of the triangle. What that means is it goes through a vertex, and it cuts the opposite side of the vertex exactly into two equal pieces. So here we have three medians of this triangle, and where those medians intersect is called the triangle's centroid. And the centroid of a triangle is where its center of mass is located. Now I think that's pretty obvious on an equilateral triangle, but it's not so obvious on a scalene triangle. So let's work our way up to that. We've had the equilateral one, that was the easy one, through here, and through here, and these are all lines of symmetry, so the center of mass had to be here. For an isosceles triangle, there's only one line of symmetry. That's down here. So we know that the center of mass must be on here somewhere, because this side, the area here, is equal to the area here, and if it's a uniform 2D shape, then that means the mass here is equal to the mass here, so the center of mass must lie along this line. Now what we're saying with the median of a triangle is something very similar. It's not quite the same though. It's not a line of symmetry, but if it goes through this vertex and it cuts the opposite side in half, then you know from your triangle work that these areas are still equal, even if the shapes are not congruent. If you tilt your head to one side and you say this is the base times the perpendicular height divided by 2 for the area of this section, then this base times that same perpendicular height, even though the point overhangs the base slightly, divided by 2, so we get the same area for this side as we do for this side, and that's because they share the same perpendicular height and they've got an equal size base. So although they're not congruent and this is not a line of symmetry, it does cut the triangle into two equal pieces by area, which on a uniform lamina means it's cutting it in half by mass. And it's the same with the third median, cutting through this vertex and cutting this side exactly in half. Comes down like this, and we get the centroid here, which is where the center of mass lies. And all of this applies to a general scalene triangle. We don't need any lines of symmetry on a triangular lamina because we can use the medians. So going from here, halfway on this edge, like this, from this corner, halfway on this edge, like this, and from this corner, or vertex, to halfway along this edge, we get our centroid, which is where the center of mass is. The center of mass of any uniform triangular lamina is located at its centroid, which is where the medians intersect. And the coordinates of this can be found by taking the mean, the average, of the coordinates of the three vertices. So if I put on general coordinates here, x1, y1, x2, y2, and x3, y3, then the xy coordinate of G is simply the average. These three added together divide by 3, these three added together divide by 3. This is the x coordinate and this is the y coordinate of the center of mass of a triangular lamina. I think the rectangle and the circle are quite easy. This one you need to remember. And then we do have one more, and this final one is the center of mass for a uniform sector of a circle and this is more complicated, but you don't need to remember it, it's in the formula booklet. However, there are some particular things that you need to be aware of about this formula, so we're going to go through it. Obviously, there is a line of symmetry here, going along this way, like this. And G must lie on this line of symmetry. Then if we call this bit O, the center of what would be the full circle, then the angle we're about to use in the formula is not this full angle, but half of that. So I need to label just half of that as alpha. Then I can intuitively put G somewhere down here-ish. And then here's the formula in the formula book. The sector of a circle at the bottom here, radius r, oh, I haven't put that on, radius r, angle at the center is 2 alpha, which is why I've labeled this as alpha, so the full angle there is 2 alpha. Then the formula for the center of mass is this, 2 times the radius times sine of alpha divided by 3 alpha from the center. So it's starting at the center and it's giving us this distance here. Now the final thing to be very careful of is that alpha must be in radians. Now usually that's a preference, because when you put it into a trig function it doesn't really make any difference so long as your calculator is in the right mode, but here we have alpha not in a trig function. So if you put degrees in here, you're just going to get the wrong answer. It must be in radians. This is the final standard result we're going to look at, and we're not going to look at where this formula comes from. I'm just going to leave it at it's in the formula book. The triangular lamina is here, but it's not giving you very much information. It just says 2/3 of the way along the median from the vertex. It doesn't give any reminder that you're taking the average of the coordinates to find where that is. And then the circular arc, that's for frameworks. So a quick summary of all of these. The center of mass of a uniform rectangular lamina is at its geometric center. For a uniform circular lamina, sometimes called a disk, that is also at its geometric center. For a uniform triangular lamina, it is at its centroid, which is 2/3 from the vertex along the median, and the coordinates of that are given here, given the coordinates of each of the vertices. For a uniform sector of a circle, it is in the formula booklet, this formula here, and it's measured from the center of the circle along the line of symmetry. The examples at the end here are not too difficult, because a lot of this is building up to the next video, where we will have some more involved examples. So a uniform triangular lamina has vertices these. Find the coordinates of its center of mass. So this is the one that you've got to remember. And that is simply that the coordinates are an average of the x-coordinates and an average of the y-coordinates. Putting the numbers in, we get 1 plus 3 plus 5 over 3, 4 plus 2 plus 3 over 3, and that gives us a 9 over 3 and another 9 over 3. So that gives final coordinates 3, 3 for the center of mass of that triangular lamina. Second example, find the center of mass of this uniform triangular lamina. We're getting a lot of triangles here because the rectangles and the circles aren't really very interesting, and this one is a little bit more interesting. Here we're going to put on our own coordinate grid, so I'll choose P as my origin point, so the x-axis is over here, and the y-axis is up here. That gives me coordinates 0, 0 for P, for Q, 2a, 0, for R, 0, a. And then I just do the same thing. We are taking the x-coordinate of each and finding the average. So we've got 0 for P, 2a for Q, 0 for R, divided by 3. And then the y-coordinates, 0 for P, 0 for Q, and a for R, divided by 3. That gives coordinates of 2/3 a and 1/3 a. However, there is a little note in the textbook that I think is worth mentioning. The original question didn't have the coordinate axes, so in terms of the original information given, giving coordinates doesn't really make a lot of sense. What you should do now with this is to relate it back to the edges of the triangle. So the x-coordinate, or what I've called the x-coordinate here, is the distance from the side RP. So if I was being really careful, that's how I would write it. So our centre of mass is 2/3 A from RP, and it's 1/3 A from the side PQ. Just because of how the question was given to us, this is a better way of putting it than coordinates. Final example for the video: find the centre of mass of a uniform quarter circle lamina of radius 8 centimeters and centre O. So if we've got a quarter circle here, something like that, slightly shaky drawing, and it's 8 centimeters radius, centre O, line of symmetry here, G is somewhere around here, and because it's a quarter circle, I know alpha as well. This is 90 degrees, but I need to work in radians, so I'll call that pi by 2. So alpha is pi by 4. So I would write it on as alpha there, pi by 4, because if I write pi by 2, there's a chance that I'll make a mistake by putting pi by 2 into the formula. Now we need the formula, so let's turn to that page in the formula booklet and simply write it down. 2r sine alpha over 3 alpha, where r is 8 and alpha is pi by 4. Sine of pi by 4 is root 2 over 2, and then tidying up the fractions gives 32 root 2 over 3 pi as an exact answer, or 4.801 ... in decimal form. Now here I should be a little bit more careful about how I write my answer. What does this distance mean? Well, we know what it means because we've talked it through. It means the distance from here to here. But how does the examiner know that that's what you mean? To make it clear for him or her, what you should do is say from O, or from the center, along the line of symmetry. Now I think you would probably be okay in this case if you simply wrote OG here. And that's because writing OG makes it clear that it's coming from O to G, that's in this bit, and coming along the line of symmetry is clear on my diagram because I've drawn G on the line of symmetry very clearly. So I think if you didn't want to write this, you could write OG, so long as your diagram made it clear that G was on the line of symmetry. And that is it for this video. I hope that's enough for you to have a go at exercise 3C, and maybe I'll see you for composite laminas in the next video.